This is the roller coaster problem. So the purpose of this activity is to calculate the mechanical energy of a cart or a marble going along different roller coaster tracks. So use the video to complete this assignment. Of course, I'm going to post this video, and then of course I post a couple of other videos that might help you out along with this assignment. So let's just take a look at this first one. So a marble has a mass of 6 kilograms and starts at rest and rolls down the track. The heights of the poles are HA is 20 meters, HB is 15, HC is 5, HD is 10, HE is the same height as C. Fill out the chart for the mechanical energy at the different points along the track. So the first thing that I want to do is I just want to fill in the information that I know. So I'm just going to fill in the heights at the different points. So HA is 20, okay. HB is 15. HC is 5. HD is 10. And you can see that HE is the same height as HC. So that's going to be 5. There we go. All right. So notice I didn't put any units. That's just save a space. But all of these are going to be in meters. All right, so first thing that I want to do is I want to look at point A, right? So I know I'm going to calculate and actually, you know what? Before I do that, what I can do is I can just calculate the elastic potential energy. You can see the equations are up here. I don't have any elastic potential energy. Nothing's being stretched or compressed, so I get 0, 0, 0, 0, 0, right? So there are some where I have the marble compressing a spring, but I'm not going to have that here. Now, I give you a hint here. The mechanical energy is the same at every point along the track. Remember, you cannot create or destroy energy. Calculate the gravitational potential energy at each point, and the rest will be kinetic energy. So let's just take a look at this, right? Let's look at point A. So the gravitational potential energy is mass times gravity times height. I know the mass, 6 kilograms. So I'm going to come over here to this calculator. 6 times, now gravity, yes, it's 9.8, right? We're going to use 10 just because that makes the math a lot easier. You could use 9.8, but for this, in order to counter we can use 10. And I do have some activities where 9.8 would work, but we're just going to use 10 just because it's easier. And then, of course, we multiply it by the height, which is 20, right? So 1,200 joules. So that's going to be my gravitational potential energy, 1,200 joules. Now, it says it starts at rest, 0, right? The velocity is going to be 0. So that means the kinetic energy, 1/2 times mass times velocity squared. Well, if the velocity is 0, well, I have 0 kinetic energy. Now, the mechanical energy is going to be the kinetic plus gravitational plus elastic. So I'm going to get 1,200. 12, 1,200, right? Good. And you can see that my graph is automatically going to update. Now, I can go ahead and put 1,200 joules for every point of mechanical energy because I know that it's going to have the same amount of mechanical energy. Now, here's what I need to do. I need to go in and let's just do point B, right? So point B, I know the total amount, right? But now I can calculate the gravitational potential energy. So the gravitational potential energy is mass, which is still 6, times gravity, which we're using 10, times the height, which at point B is going to be 15, right? So I already have that up there. 15 equals 900, right? So my gravitational potential energy is 900 joules of gravitational potential energy. Now, the rest of that energy, right? If I have to look at my equation for mechanical energy, the rest of that energy is kinetic energy. So I take that 1,200 mechanical energy and I subtract the gravitational potential energy, which is 900. And what I have left over is that 300. 300. So now that I know the kinetic energy, I can use my equation for kinetic energy, 1/2 times mass times velocity squared, to solve for the velocity at that point. So that's what you're going to do for all of these points. And you'll see I like this because it's got the graphic here of what this roller coaster is going to look like with the track, and it's going to automatically update a graph so I can visualize the different forms of energy. But I know the mechanical energy is going to remain the same. The total amount is going to remain the same. So you can see that there's another problem. 2 looks very similar. Now on problem 3, now I have a spring. So now I've got an elastic potential energy at that last point. It compresses the spring. You can calculate how far back that spring is compressed. Next one is a little bit tricky. The next one, it does have an initial velocity at point A. So in order to find that mechanical energy, you can see I give you a little hint here. It does have both kinetic and gravitational. So you're going to have to calculate both of those, add them to find the total amount of mechanical energy. Now, the roller coaster design, these are asking about the like maximum velocity. So that first one says, okay, I give you all the heights to this marble. I want you to calculate what is the minimum velocity that this marble has to be going in order to make it over the tallest point. So that way it doesn't roll back down. So there is a large hint here that will help you out. But also that's looking at the equation. That's realizing, and the big hint here is that the mechanical energy is the same at every single point, the total amount. But what types are going to vary? And then the next one says, okay, great. Now I've got this marble rolling. Well, what's the maximum height that this roller coaster can have, right? So that's doing the same thing, realizing the mechanical energy is the same at every single point, and just saying, okay, great. Now I know the mechanical energy at the start. What's the highest point that this can be at? And I tell you how to do that in the hints. And then down here, just the last one, explain why the velocity of an object on a roller coaster track is mass independent. So that's just looking at the equations, and there is a little hint there for you. And the last one is explain what limits the tallest point on a roller coaster. And as always, I do give you a little bit of a hint there for that. So these are all the different problems, like types of problems that you can have for a roller coaster. Very good way to visualize mechanical energy transforming from one form to the other. So once again, this is the class activity, those roller coaster problems.